Good evening and welcome to the first lecture in the 2023 Science for Alaska Talk series. Tonight we're going to be bringing you research professor Paul A. Bernhardt, who's going to be talking about detecting space debris bullets. Now, you can't really see this from back there, but I really am smiling because we actually have an audience in front of us this time for the first time in a couple of years, and it's very nice. Yeah. The last 2 years, we were online only, and so I'm going to say hi to our online audience back in that camera. I know they're there, but I can't see them. So anyway, this is our first time with two audiences, one in person and one online from all over the place. So if this is your first time with us, we're glad to have you here, and if you've been with us in past years, we're glad to have you back. I'm Rod Boyce with the Geophysical Institute's Public Information Office. Before we go a little further tonight, I want to acknowledge the Alaska Native nations upon whose ancestral lands we are located tonight and where our campuses reside. In Fairbanks, our Trothieta campus, where we are, is on the ancestral lands of the Dene people of the lower Tanana River. Tonight, we're happy to be able to be back in person, as I said, and have our online audience. This is our 31st year of the lecture series, and they're going to be every week, Tuesday at 7 through March 7th. The lecture series this year is supported by the Geophysical Institute, Alaska EPSCoR, the Triple Horn family, Vic and Vicki Weinstein, and Lifewater Engineering Company. And as you know, it's sponsors that make things happen, and so we're very grateful for what they allow us to do here. Just a few quick announcements I have to read off to you tonight. If you have a cell phone, now would be a great time to silence it, and I've done that already, okay? So please do that. That way you're not going to disturb your neighbors or our presenter this evening. The lecture is being recorded. The video will be available for viewing online at the GI's website and the YouTube channel shortly. Restrooms, important information, are located outside the auditorium. There's one to the right and others around the hallway off to this side. There's an emergency exit out back of the room, and regular exits are to the left and right at the top of the stairs where you came in. As you entered, you were handed a piece of paper that has a survey on how you heard about the lectures, and we would really love it to have you fill that out. You can leave it with us as you leave tonight. On the back side of that form, this one right here, if you don't have one, we can get one to you. You can stick up your hand. On the back, you can find a spot to write questions you might like to ask our presenter this evening. Also on that piece of paper is a QR code that you can scan to get live captions. That's the first time we're doing that this year on your smartphone or other device. The formal lecture will last about 45 minutes. There will be time for some questions afterward, and we hope you do have some. You may raise your hand to ask the questions verbally, and either myself or my colleague Ray over here will bring a microphone to you, or you can hand us your card with the question on it, and we'd be happy to read it out for you. If we do not have time for all questions, you can leave your questions with us on that form at the end of the evening, and we'll be sure to try and get those answered for you. So, with all those announcements out of the way, I would like to introduce Dr. Robert McCoy, who is director of the Geophysical Institute, and he will welcome tonight's speaker.
It's my pleasure to introduce Paul Bernhardt. As Rod already said, Paul's a research professor in the Geophysical Institute. He's also the chief scientist at HARP. Paul's been here since 2022. His background, he got a BS in electrical engineering, I think, from the University of California, Santa Barbara, a long time ago. Followed a couple years later with a MS from Stanford and EE, and finally a PhD at Stanford in 1976. Prior to coming to Alaska, Paul spent a little over 30 years at the Naval Research Lab in the Plasma Physics Division at NRL in DC, and he was head of the Space Use and Plasma Environment Research, SUPER, that's the acronym, section head at NRL. Prior to that, he was a staff member at Los Alamos National Laboratory from like 81 to 88, and a senior research associate before that at Stanford University up to about 1980. Paul has published 170 papers in refereed journals, and he's a fellow of both the Institute of Electrical and Electronic Engineers and the American Physical Society. Paul's science interests include theoretical and observational studies of the upper atmosphere and the ionosphere. He uses high-power radio waves, chemical releases in space, sounding rocket, satellite, and space shuttle experiments. And Paul's going to tell you about some of this stuff right now. Paul?
So I have a question. How many of you had high school physics? Raise your hand. Keep it up. Keep them up. Keep them up. Now, how many of you know how to shoot a gun? I thought that would cover everybody, because one of those two is either a requirement for this talk. So I'm talking about space bullets, which are debris that is produced when a satellite collides with another satellite, or when they test various weapons on satellites, or a dead satellite, just a satellite that just ran out of batteries and no longer is used. Those are all space debris. And they're moving faster than a bullet, much faster than a bullet, maybe 3 or 4 times faster bullet. And if they happen to hit another satellite that is sort of stationary or moving in a different path, they can do some damage. So could I have the first slide? How do I do that? Do I do something here? Now something has to be clever here. Very good, good. There we go. So, oh, thanks. So, there's some objects up here, Iridium and Starlink. Now, you guys probably think those are satellites. To me, they're space objects. They're objects that we can use for science. And what we try to do is see what happens when those objects get near another satellite that has a set of instruments called EPOP. Now these booms on there are electric field sensors. So if that satellite has some electric fields it makes, it can be measured by the EPOP sensor. And the collaborators on this talk are primarily Canadians. The University of Calgary runs that particular satellite with the EPOP sensors, and then the very clever fellow thought of this idea from DRDC Ottawa. His name is Lauchie Scott, and people were talking for a number of years that detecting space debris may involve waves in the ionospheric plasma, and he said, well, why don't we just measure them? As I say, there's been about 10 years of theory, and finally somebody said, well, let's see if we can measure this. And that's what I'm talking about today. And then Rob Pfaff and Bob Holsworth are people who work with us to measure electric fields. Okay, I'll try this, see if this works. Awesome. So, space debris, sources, and hazards. As I said, space debris is either obsolete satellites or satellite collisions. And why do we care? Well, one is optical interference. If you have a telescope and you want to make a nice picture of Saturn, and all of a sudden one of these pieces of space debris goes in, you have a white line across there from scattered sunlight. And then, as I mentioned, if one satellite runs into your satellite, that's not good either. So there's various classical space debris detection techniques are optical sensors with scattered light waves, or radars with scattered electromagnetic waves. So the light hits the piece of space debris, or the radio wave hits a piece of space debris, it scatters off, and you measure its position by looking where that occurs. The new concepts we are coming up with is proximity detection from generated plasma waves. So this object going through space, maybe charges, go through a plasma, go across the magnetic fields, and makes various plasma waves. And so we also look at remote detection of scatter from the plasma waves. So you could have this cloud of plasma waves involved with your satellite, but then you could send up another signal, like a radio signal, and try to scatter off those plasma waves. So we're exploring those techniques. So now I've heard use the word waves about 8 times, so I have to give you the quick tutorial on waves. Where we're standing right now, there's only 2 waves. There's sound waves and light waves. And that's great. And people on the Earth have it easy because they only have to worry about 2 waves. However, if you're on the ocean and you have gravity, you have buoyancy waves. Okay, so we're only down to 3 waves. We can handle that. Immediately when you go into a plasma, it just becomes horribly complex. A plasma is composed of an electron and an ion, and these then accumulate, and then you get an electron gas and ion gas. So all of the other waves you've had, you also have something called electron and ion plasma waves. And these are the waves of interacting between the electrons and the ions. So let's say you have an electron here and he's all happy, and you just push it this way and let it go. He's going to try to go back to where he was in equilibrium, but then he's going to oscillate. That's the plasma frequency. Same with the ions. The next is waves in a cold electron, that's a cold electron ion plasma. With a warm electron ion plasma, you start to have sound waves. You have ion sound waves, electron sound waves, and then ion acoustic waves. These are waves that couple the electrons and the ions together because they have forces between them. And then you get a wave that's sort of a hybrid with the sound waves, and that's the ion acoustic wave. Finally, you throw in a magnetic field, and then you just go home. You quit. We're done. We don't want to do any more science because you have electrostatic ion and electron cyclotron waves. The nice thing about magnetic fields are that if you push an electron along the magnetic field, it's just like not having the magnetic field there. But when you try to push it across, you push it this way, and it goes this way. And then it goes this way, and it actually goes around the magnetic field. Now, how many of you have ever drilled a hole in a metal plate and want to enlarge the hole? Yes. So, you know, if you're like me, you just lift up the piece of metal and you push it against the bit in the drill press, and you want it to go this way, and the plate goes this way. I'm sure you've all experienced that. So that's exactly what's going on here. The force is different than the direction you're pushing. Finally, you have the electromagnetic, the magnetohydrodynamic MHD waves and the Whistler waves. And this is waves that are associated with the magnetic field lines. Now, magnetic field lines are like guitar strings. Wait a minute, I saw something back here. What is this thing? So you can imagine, and I have to hold it up so the camera can see this. You have to imagine that you have, let's say, one of our satellites trying to go along the guitar string. It doesn't make much noise. Makes a little bit of noise, but it loves to go, and there's not much. But now, in a different environment, which is most of the time, these space debris, they go across the magnetic field lines, and they'll pluck it. But there's electrons and there's ions, so you get 2 different frequencies at the same time. Actually, you get a whole host of frequencies with the space debris going across the magnetic field lines. So that's what I want to talk about today. What kind of waves are produced when satellite goes through the plasma across magnetic field lines? Well, let's start out, when I was born, not when you guys were born, we're young people, when I was born, there weren't any satellites up there at all. 1949 was I was born. And then around 1960 or 59, 58, Sputnik was launched. And then it's just taken off. And these are the number of known objects. And they're grouped as total objects, space debris, spacecraft, mission-related debris, and rocket bodies, a bunch of stuff. And then occasionally they bump up. And that's when either somebody decides to take a weapon and shoot at a satellite just to see what's going to happen, and that gives you 2,000 more pieces of space debris. Or when 2 satellites collide together, accidentally, and that makes a couple more thousand pieces of space debris. So you want to avoid those things. You want to avoid trying to shoot satellites, and you want to avoid trying to collide with satellites. The problem is, these are the known objects, but there's actually 1 million of unknown objects, mainly because they're too small to be seen with optics or radar. So our program is to try to detect those really small little guys. So this is the sensor operations chart for something we call SOIMO, Space Object Identification with Measurements of Orbit-Driven Waves. Sounds like something you'd eat at a restaurant. Anyway, SOIMO, remember that. Okay, so the target excitation can be light, it can be radar waves, or you can excite it with high power HF illumination like the HARP facility, with low frequency Whistler waves, or just the motion of the object itself through the plasma. So those are the source of excitation. The satellite types are space object with rocket propulsion, with ion thrusters, or no propulsion. And then finally, the sensors are ground optical sensors like telescopes, ground radar receivers, receivers on satellites, and some of the lower frequency receivers on satellite. So these are non-traditional techniques that we're developing at the University of Alaska with both NASA and other sponsors for detection and diagnostics. So we're actually doing something that people do all the time with meteors. We're trying to detect space objects, but a meteor is a space object. It just happens to enter the atmosphere and make a big display. They're hypersonic. They go from 5 to 12 kilometers a second, and they move through the stratosphere, the mesosphere, and the lower thermosphere. And the one thing you do is, once they get into the atmosphere, they glow, and you take a picture of it. And this is from the NASA all-sky fireball imager of a meteor, optical emissions with radiation from the neutral particles. Another thing you do, of course, is that you make hot ion and hot electron from the hot neutrals, and that gives you a plasma plume that could scatter radio waves. So you get a nice radar signature, and this is from my colleague Koki Chow from Peru, but he's in Germany now, with the Marcy radar, and you get different components. The head means the whole body of the meteor scatters the radar. Then you also get specular, which means you get a trail. And then if you're perpendicular to trail, you get a very enhanced scatter. And then non-specular is you actually scatter off the field line irregularities that are in the plasma. So we can get all of this with space debris. Now there's another thing. If you look at this image, this is actually radio emissions from the meteor itself. And nobody in this room knew about this until they came here, unless maybe Christine did, I'm sure she did. But everybody knew about it. Should know this. A radio signal comes off a meteor when it enters the atmosphere. And this was discovered by Keith Obenberger using the long wavelength array up in Socorro, New Mexico. So we're taking this approach, that an object going through the atmosphere can radiate signals. And maybe you can see those at a distance. So maybe a satellite would do the same thing. Oh, I just want to, so the signals are at 38 megahertz. So it's like a nice low frequency. Okay, so this is all the objects in space, and the interesting process is that satellites and space debris all reside in a plasma. The extra contours in there are the contours of the ionosphere. So every space object that we have goes through a plasma. Now that's where the plasma physics come in, that's where the plasma waves come in. So let's look at a few examples of using various sensors to measure space objects accidentally. This is at the Arecibo Observatory in Puerto Rico. The very thin line is the 430 megahertz UHF radar, the most powerful, let's say, incoherent scatter radar ever built. And lo and behold, the space station went right through that beam. The big fat beam is the Arecibo version of HARP, by the way, but we're focusing on the UHF radar there, and that's a signal right there from scattering. And if you look at it carefully, by the way, the ambient curve there is the scatter from the ionosphere, and it's actually telling you what the electron density is, and the bottom you have the temperatures. The enhanced scatter is from the target, But if you really look carefully, or if you circle it, there's an ionacoustic disturbance associated with the space station moving through the plasma that's scattering. So it leaves a wake. It leaves a wake as it moves through the plasma. So we decided to enlist the Canadian Swarm-E satellite. It used to be called Cassiope, then CSA and ESA got involved, and now it's called Swarm-E. It has a number of instruments, but we're going to talk a little bit about the fast auroral imager and mainly about the electric field receiver. So this is a picture of the aurora over Alaska, over Fairbanks, from Swarm-E, from the FAI. And you see some nice auroral pictures, and if you look carefully, there's some stars up there too, and that was the trajectory of the satellite that was measuring the aurora. This is a similar picture looking up in the sky very recently, and you see stars, but then you see these things flying through that. And they're sort of regular, and they're satellites. So this is a very useful way of using an imager in space to detect the presence of satellites. My buddy, Andy Nicholas. Now, how many in this room, raise your hand if you've ever heard of Andy Nicholas? Okay, he graduated from UAF. He's at the Naval Research Lab, and he has a design, along with the other people in space science, of a laser system that's going to scatter laser in a big disk, and then when space debris, very small space debris, go through that disk to scatter light. And it's a system that uses a 1-watt laser. It measures 1 micron to 100 millimeter. In other words, really small guys to somewhat bigger guys at ranges out to 30 meters. So we want to see if our plasma wave technique can be, let's say, compatible or complementary to this technique to measure the space debris. So what we're going to do is crash satellites. Well, they crash anyway. They almost crash. And so what we're going to do is have a host satellite with a receiver and a target satellite that makes what I call an entrained plasma wave cloud. So as the satellite moves, this plasma wave cloud moves with it. And so we're looking into plasma wave generation, wave coupling, wave propagation away from the source, and then wave detection. Now, since earlier I explained all about plasma waves and how easy they were, I have to put this list up. Otherwise, you would have been running out of the room if I hadn't done that great explanation of the fast magnetosonic, the alphane, the slow magnetosonic, Whistler, ion cyclotron, ionacoustic, and lower hybrid waves. And they all have various aliases, frequency ranges, speed, group direction, and polarization. By polarization means you have an electric field this way, and if your antenna is orthogonal to that, you're not going to see anything. If it's aligned with it, you'll see it. So these are properties of the waves, but I just thought that's sort of boring. So why don't I just show you some waves? So we're going to use our friend HARP, and we're going to just turn on HARP, and the electromagnetic beam is going to interact with the ionosphere, and depending on what frequency we use, what its relationship is to the magnetic gyro frequency, electron cyclotron frequency, or harmonics, and the direction, we can excite various waves at our command, any of these waves. And then we make emissions, it's called stimulated electromagnetic emissions, that are received on the ground with a receiver. So now you know what HARP does. It's to verify the presence of plasma waves in the ionosphere. So the first we're going to start out with this ionacoustic or slow MHD wave. So that's what happens when you turn on HARP. And the pump is the electromagnetic signal that you put up there, and this is frequency versus power. The downshifted, it's called stimulated Brillouin scatter 1 mode, is the thing you just heard. Normally, if that didn't occur, you wouldn't have heard anything. So that's what that wave sounds like. And the other wave, it's another SBS2, which is at a different altitude. And then finally, we're going to go to the ion cyclotron mode, which is a very well-controlled, narrow frequency. And it sounds like it's sending Morse code. Yeah, I should give that to a ham operator and see if he could decode it. But it's just, what it is the wave goes off, and then it sucks all the energy, and then it goes out, and it comes back on, so it's coming off and on. Finally, we go to the lower hybrid frequency, ion acoustic frequency, and then my favorite mode is the ion Bernstein mode. These are harmonics of the ion cyclotron frequency. And what does this sound like to you? This is a question for the audience. How many of you ever blown on a tube about that long? You blow on it, it makes a harmonic, the second harmonic, third harmonic. So that's why all the harmonics are in that mode. So anyways, it's good fun, and as I say, we can make these waves at will. Another way you can make waves is by putting a whole bunch of energy localized in the plasma. So we use an ancient vehicle called the Space Shuttle, and it's been retired. I have the honor of having been born before the Space Shuttle, and I've lasted till after the Space Shuttle, and I miss the Space Shuttle because we were able to have dedicated engine burns. And this one is, we took a target Space Shuttle and we shot it at the host CNOF satellites, was Air Force satellites. So NASA shoots Air Force satellites with rocket exhaust. And we pointed the engine at it and we fired the exhaust. Sorry, I don't want to go through that again. Okay, and you see the lower left, the cloud of exhaust engulfs the spacecraft. So now the electric field instrument called VFI on CNOFs measured the electric fields produced after we turned on the engine. Now you turn on the engine, and you make a whistler. Yeah, we'll explain whistlers later. And you turn off the engine, and you make another whistler. That was turning off the engine. And then you wait there, and this cloud is coming towards you of exhaust, charge exchanging, making lower hybrid waves, making ion acoustic waves, and you're on the CNOF satellite, and you're holding, because it's engulfing you. And then the cloud goes by, and everybody's happy again. So this is a whole, you've heard every electromagnetic or plasma wave, electrostatic and electromagnetic plasma wave that we can make, and now you're very familiar with them. So let's see if we can make them by just the satellite themselves. So one idea is, and the question came up, well, is there sort of a acoustic shock, an ion acoustic shock formed around the satellite as it moves hypersonically through the plasma, and then can you fly your sensor trajectory through that shock? That was the first idea. Then the second idea was they looked carefully at the physics, and they discovered that possibly you could produce solitons. And these are solitary waves that follow, and a structure that follows the spacecraft itself, and actually called a precursor is actually in front of the structure. And then the question is, can you fly a sensor through that? If you look carefully at the measurement distances here, these are in centimeters. So 10 centimeters is about this. And so the answer is, you have to be really close to fly through that. So then we decided to take our Swarm-E satellite and look at a bunch of, fortunately, we have so many of these other satellites that we can wait till they fly close to each other. The top left is all the Starlinks. How many of you knew that there's 2,700 Starlinks in orbit? Yes. Well, I didn't notice, or it's actually it just changed. It's 3,271. As we were speaking, it just changed. The other one is the OneWeb satellites. There's 544 of them. Now we start getting into the debris, the Iridium-33 debris that collided with the Cosmo 2251. There's 657 pieces of those. The Chinese anti-set test made 3,532 pieces of debris. The Cosmic after colliding with iridium, has a 1715. And finally, the Cosmos debris, this was another anti-sat test, was 1789. So fortunately for us who are doing this physics, everybody's making space debris, including Starlink. Okay, do I say Starlink space debris? No, but it's a wonderful satellite that we can fly next to. So this is Starlink, and this is our program. We're just going to zip right past the satellite and see as close as we can. And our criterion, it had to come in within 1 kilometer of the satellite. And let's see what kind of waves we produce. The other thing we had to worry about, the Starlink has these ion thrusters. So we were trying to look at inert satellites. So if they have the ion thruster going, that's cheating. So after we make our measurements, we call up Starlink. We sort of know the president of Starlink. And he said, no, we weren't doing the thruster. So anyway, these are the satellite themselves making that. Okay, we're crashing, and this is the ambient noise in the upper atmosphere. Those are whistlers. And those are made by lightning. Now, are you grabbing onto the chair? The satellites are going to get close to each other, and we're going to get a little enhancement of the noise. Okay, so we're going through the cloud of noise around the Starlink, and then as we keep going, we have all these whistlers. So that's the problem. Detecting that as opposed to the natural environment is the problem with this. But you can see, it turns out it's easy because I'll show you in the next slide. And then you're moving away from the satellites. Now that range is about 50 kilometers. So the radius of cloud of noise around that particular event was about 50 kilometers. And that's pretty big. And then it slowly decays away as the satellites move away. So that worked okay with Starlink. So let's try this one. This is a Cosmos 2251 space debris. And this was 1 square meter. This is 0.02 square meters. So it's a much smaller object. And as you see, it makes a much smaller signature. This is iridium. This is just an iridium satellite. And it was fortunately nice and quiet. It's fine, it's fine. Yeah, it keeps the audience awake. No sleeping in this talk. So now we're going in the environment of the iridium satellite. I think he's worried that the speaker's going to blow out, but I think it's okay. And then it goes away. So these are the kind of measurements we discovered because the one Canadian fellow said, why don't we fly this satellite close to other satellites? There was a little whistler at the end there. Okay, great. And then finally, that's another Starlink. So it looks sort of, if you do a few measurements, that all Starlinks look alike in terms of their noise spectrum or noise waveforms, but that's one, they're all at the same altitude. So they have about the same plasma density and they're all the same shape. So we also discovered that this primarily or maybe only occurs if you're moving across magnetic field lines. How many remember, like 5 hours ago, I said, moving along field lines, you don't even see the field lines. Moving across, that's the secret. Okay, so this is just an encounter between the Starlink satellite and the EPOP instrumentation. And that's the spectrum, and that's some of the conclusions. But you see the spectrum goes between about 0 to 5 kilohertz, which is above the ion cyclotron frequency up to something called the lower hybrid frequency in the media. And then you'll see extending up above that is some smaller noise, which may be whistlers. So that's why I spent hours on this plasma wave stuff. So now we have some data and we can interpret it. and the range is about 50 kilometers on that one. Here's the other one, which is the conjunction of the Cosmos 2251 space debris, the small piece of space debris. And this is a measurement. Okay, so one antenna saw nothing. The other one saw a nice signature. So that tells us it's polarized. That tells you what the mode is, and that's our conclusions. Again, this was a 100 millimeter object that saw something out to 90 kilometers. So there's some hope that this may be a useful concept. So the first thing you do is you go back to the lab, your office and run some simulations. And as I said, there's so many waves, we decided let's just pick an Alfvén wave. That's the simplest wave. That's the wave that goes along the field lines. And we ran a Cherenkov radiation code that was produced by George Morales and his students at UCLA. The left picture is for the satellite moving along the field lines. And look at the scale. The scale is 0 to 10 kilometers along the field line and minus 40 to plus 40 meters. So I've expanded the scale vertically. So it's really a thin little guy that is being produced with sort of a plasma wave trail behind it. So now let's tilt the magnetic field by 90 degrees. So let's just bang on that magnetic field line. And you see it sends waves plus or minus 20 kilometers away from the spacecraft. And it makes a plasma Alfvén region that is following the spacecraft itself. This is only one of these 8 waves that I show you. So we have a lot of work to do to model all the different circumstances to identify this wave phenomenon. Okay, so now the question is, what if you don't want to go into space? What if you want to sit on the ground and measure the presence of a satellite with this phenomenon? Well, I'm at UAF, so I have to use HARP. That's a requirement at UAF. You have to use HARP to do your work. So this is a HARP beam. Remember early we did it and we made some waves. This is a simulation. This is actually an experiment, not with a satellite, but trying to simulate a satellite going through the HARP beam. So here it is. We got to wait. There he goes. Here he's going. And then as he goes through the beam, see, the HARP itself is getting the plasma ready to be excited. Then when the satellite goes through, excites it. So this is not a measurement. This was just a test to see if we could see if it would work. And then I'm working with a group in Scotland on the simulation and on these experiments, and we're doing this type of stuff in the future. Okay, why is this difficult? One, you have to get a satellite down at 300 kilometers altitude. It has to be at high latitude, has to go over HARP. And it turns out there are about 34 satellites that fit that category. And so we're working on those experiments. So this is summary. In the past, people have made various simulations of what the plasma wave environment would be. We, as I said, with our help from the Canadians, decided, why don't we just measure something? And then instead of all these different simulations, we can focus on one that represents our experimental conditions. And finally, in the future, we're planning to put up a SOIMO-SAT. Remember SOIMO, the name of this whole program, and that'll be a 3-axis electric field measurement system to actually fly around and looking for space debris in different satellites. So in summary, SOIMO implications for society. Why would anybody here care? Well, first of all, finding small space debris using plasma waves is complementary to the standard techniques. And so we can take our swarmy satellite, which is an optical sensor, and also turn on the electric field sensor at the same time, so we could actually see the satellite we're measuring the electric fields from. We've demonstrated with some small objects, and the application goal, instead of 100 millimeters, we want to go down to 1 millimeter, because those are still bullets. And so we want to find out those guys. Alaska should be concerned because there's an increasing number of satellites. Starlink proposes to put 30,000 satellites in orbit, to do the internet functions. Well, that's good. Starlink provides internet for remote areas, like out in the middle of the Alaska wilderness. However, anybody who wants to do astronomy is going to see things like the picture in the upper right. That's an actual picture of Starlink going through a star image. And auroral viewing, you're watching your aurora and all of a sudden you see this stuff come through. Hey, it might be interesting, but it might have some consequences. So large satellite constellations need to avoid collisions. So this requires accurate monitoring of the space objects and then firing thrusters so you dodge the bullets. So all these things, 30,000 are going up there. If they get closer, you got to turn on that ion thruster and get it out of there. And so what we think, and we have a proposal out to NASA, is we need to assess the impact of space debris and ion beams on space. What is that going to happen? Just, if an astronomer, gets his picture messed up, well, that's not our job. Our job is space science. How is all these ion beams injected into the upper atmosphere? And so offline, we have some ideas what's going to happen. So we'd like to do research on that. So future research is continued swarmy operations with electric field sensing and optical imagery at the same time, which we haven't done yet. We also have a laboratory component working with Naval Research Lab in West Virginia University to set up a space plasma system in a chamber and try to see if hypersonic objects will launch the waves. We want to do enhanced computation of plasma waves, similar to the early stuff we did, but just looking at all the other effects of charged objects. And finally, do 3D models of whistlers, shear and compressional alpha waves from space debris. So thank you for your kind attention. And I have to ask the question, how do I do time-wise?
You're doing fabulous.
Good. So we're going to have some questions from the audience. Yes.
I seem to remember reading an article about the density of all of the space debris that's out there. Is there going to be, or has anybody predicted that there could possibly be a chain reaction out there, i.e., the ping pong ball with on the mouse traps, and then basically everything's going to get wiped out, and we won't be able to put anything else up into the atmosphere?
Yeah. So I don't need this because I have my own microphone, but okay. Yeah, the answer is it already happened. 2 satellites collided, made 2,000 objects, and some of those have interacted, or people have tried to dodge them. Fortunately, space is big, and so it's not like the usual, mousetrap and ping pong ball simulation. But it's a very possibility. It could mushroom and make things worse. And so there's, besides detecting, there's also remediation. How do you get rid of the space debris? And we're not, we only want to say, hey, it's over here, and then we'll let somebody else take their, mitt and try to grab it. So.
Before we get to another question, I want to tell the audience here and Paul that we have 50 people online watching you tonight, coming from, we've got a couple of locations here, a couple around Fairbanks, of course, but Tacoma, and I really don't know where East Tawas, Michigan is. So hello, and thanks for watching from East Tawas, Michigan. I hope I pronounced that correctly. All right. Any other questions for Paul?
Do you want me to run up with the microphone?
No, we've got Ray
We got
over there
runners.
is going to bring it. Yep.
Okay.
Stick your hand up again. There we go.
Thank you for the presentation. I've been very curious about how or who has jurisdiction about objects in space. We know that there are certain parameters about how far out our geographic boundaries are, and I don't know if there is any entity that tries to deal with issues like space trash. It's going to become even more complex as we try to wire everyone and we try to get satellite coverage every place, and there doesn't seem to be any way to keep all these companies from putting more things up there. I don't know what their liabilities are, and who would determine that?
Yeah. I agree that it should be studied. I don't think that it's always hazardous, but you should study it, and sometimes there may be even beneficial aspects of space debris. There have been studies that an organization called JASON, which is a DoD organization that likes to take big problems, and they did a study of the Starlink effect, and they focus, however, primarily on astronomy or optical systems. You know, how is it going to affect the ability to see, you know, with telescopes and things like that? And they concluded that they said up to 40,000, and it's not going to impact those systems much. I haven't seen any other studies, but as I say, I have submitted a proposal through the Geophysical Institute to just ask the question, what happens, you know, at different levels of space debris, or even space like Starlinks or OneWebs, or, you know, all the wonderful, and there's also Space Bee. Has anybody heard of Space Bee? These are these little guys. They're internet. And you know, you just have to ask the question. One is the fact that you're making waves going to impact everything? Are those waves going to be launched and interact? For instance, we've done some studies with interactions of man-made waves with the radiation belts. And I'm not going to spend hours on the radiation belts because I'll get kicked off. But does everybody know what the radiation belts are? Van Allen discovered them. And they come and a satellite flies through them, and then those are different bullets. Those are much more energetic, much smaller bullets that damage satellites. And we try to get rid of them. It turns out that the waves that man generates, these are called Whistler mode waves, actually precipitates them out and gets rid of them. So maybe if Starlink turns on its ion thruster and makes whistlers, which is very possible, or anyway, that could actually benefit man by getting rid of some of these nasty radiation belts that bother satellites. So we're not coming in saying it's bad, it's good. We're just going to say, what's the impact? And right now, I'm not aware of too many people working in that area.
Right
I
here.
could be wrong.
Yeah, well, just recently I got back from Space Center Houston, so I've seen some of the damage that these objects can do, and I'm glad that somebody's looking into other ways to detect them. My question is about HARP. Now, from a previous presentation here, I understand there's like a sister facility, I think in Adelaide, Australia or somewhere, that like you can bounce a beam off of and be received in the other hemisphere. And I'm wondering...
I don't know of it. I don't know of a sister facility, but maybe if you keep talking, I'll try to understand. There might be.
Okay, well, what I was wondering is, I mean, you're running a test like with an object going through a beam from here and you're picking up the result here.
Yes.
But has there been any thought to using that system where you, say, excite the upper atmosphere here and then pull the result off at another ground station?
Oh, yeah.
down there?
We are connected to the conjugate hemisphere by magnetic field lines, you know, the dipole field lines, and they go up. And probably you could be referring to that there is a very powerful VLF transmitter in Australia, I think maybe, and it's a 2 million watt facility, and its conjugate lands right in Russia. But Russia also has very close to it their VLF transmitter, and that lands in Australia. And it's really interesting to put a receiver there and listen to the Russian VLF transmission. And then we launch ours, and they bounce back and they bounce back, and compare those two. So the presence of these waves, and these are the waves that kick the radiation belt particles out of the radiation belts. So in my mind, at least, those are beneficial waves. And we're looking at if, you know, that maybe you fire a rocket engine over one of those transmitters, or maybe a space debris goes over one of those transmitters. That might even enhance the effectiveness of those. So we're exploring all kinds of things like that, if that
Paul,
makes sense.
I have another question right next to me here.
Oh, okay.
Thank you. I'm not sure if you can speak to this or not, but with all this debris and satellite activity and you guys shooting sound waves, if you will, up, how is that impacting those who want to listen beyond, that deep space listening that the Earth is moving through? How's this impacting that?
Impacting what?
Those who are wanting to listen to anything coming towards the Earth.
Oh, you mean like listening for extraterrestrial intelligence?
Well,
or,
just
or,
any-
or just
any-
signals from the galactic noise and things like that.
Yeah.
I don't know of any impact. I think I'm sure somebody like Bob will immediately say, no, you're wrong, there is this impact. But I don't personally, I can't think of any impact right now of that. It's not blocking anything. But we'll think about it. Okay.
All right, any other questions for Paul?
I
Ray?
have a question from online. So Keith Dunkel, who joined us on Zoom, is wondering, can you set up transmitters anywhere to detect space debris anywhere around the globe? How powerful would the transmitters have to be?
The answer is probably 1/10 of HARP would work. And why I'm saying that is we're trying to, anyway, there used to be a system at Arecibo, Puerto Rico, world's biggest radio telescope, where we had a 1/10 of HARP type power. And we have done, and I showed some of the Arecibo results from other stuff. We actually could do it with that one. So I would say 1/10 of HARP would work, maybe down to 1/100th of a HARP. But at least a 1/10 I'm sure would be a workable system.
A question on the other side of the room?
Hey, thank you for that great talk. It's very interesting. I just had a random fact question, which I figured you would know. So you said that EPOP came within a kilometer of one of the Starlinks. I mean, that was the example you showed. Does that happen a lot, that they get within a kilometer? Or is that like you had to wait 5 years to find a time when they got close enough?
Well, we've got closer than a kilometer.
On a regular basis?
Well, as I say, I love Starlink because there's 2,700 of them, and EPOP has an apogee of 1,500 and a perigee of 300, and they're all at 500. So they keep going through, and yeah, so they actually get decently close. And you're saying, will they crash into each other? Well, I don't think that Starlink is monitoring the presence of EPOP, but they haven't. I'm trying to think. The closest, yeah, I would say 400 meters was the closest, which is, as you say, that's a collision in space. Not a real collision, but it's really close. So yes.
Questions?
I got a question. I'll speak loudly. I think here. Building on Ron's point, is there any body, UN, et cetera, that actually is regulating what goes up?
Yeah. Okay. So your question is, when Elon Musk says, "I'm going to put 40,000 Starlink satellites up there," the answer is, I don't know, but I don't think so. What he has to get permission is to radiate. He gets from the FCC. He's got permission to radiate the signals that send up the internet signal and downloads it. I'm afraid I don't know, and it's always surprising to me. But Bob knows because he knows many things. And here's a nice microphone, please.
There are international agreements. Before any nation can launch a new satellite, they have to demonstrate that satellite won't be in orbit for longer than 25 years. So either it's going to encounter satellite drag and slowly spiral in, or it's going to have enough fuel on board to fire its engines and drive itself in. Or sometimes satellites, especially ones higher up, will fire their engines and move up out of the danger area.
Demonstrate
To whoever gives them permission to launch. In the U.S., all U.S. satellite makers have to get permission from the FAA, from the military, from the Air Force, and there's, like I said, international law that all nations who put things in space go by. And it's 25 years. Yeah. You have to demonstrate that.
So if I could paraphrase Bob, there is regulation on the longevity of the satellite. And this is 25 years after it's no longer useful type thing. There's no regulation on the density of the satellites that I know of. But I think that common sense would say, at least with 40,000 of anything, I don't care if it's 40,000 cars, 40,000 marbles, you gotta ask the question, is that gonna impact anything? Because it's so much more than we have right now. And we started out with no satellites. Now we're up to, as I said, 20,000 that they're operational, and then 1 million pieces of space debris. So I think it's a great question. I mean, it's an obvious question, and well, we'll see what happens.
Just to follow up on that, if you had geosynchronous, you had two different people that wanted to put the satellite in the same spot.
Oh, microphone time.
Yeah, my question, so to follow up on that, if you had a geosynchronous area that you wanted to put a satellite, but another competing country wanted to put a satellite there at the same altitude, at the same position, who would be the person to decide which country gets to do that, or is there anybody? Yeah. It's first come, first served.
I'm sure that the geosynchronous parking orbits are well regulated, and it must be an international body of some sort. But I'll have to ask Perry Mason on that one. So, some good attorney. So anyway, I don't know that. So anyway, yes.
Wait, you got to wait for the runner to come up.
This is primarily for the audience out in the on the
How
internet.
far in outer space are you trying to detect the debris? How far, like from surface of the Earth, like?
I'm sorry.
How many kilometers up from the Earth's surface are you trying to detect the debris?
Oh, as far as we can, but I should say the system devised by Andy Nicholas goes out to 100 meters or so, and we would definitely, we would think 100 kilometers would be great, And we've sort of demonstrated that occasionally. And let me tell you, first of all, I've showed you what I've called the typical best examples. In other words, there's a lot of times the two satellites get close together and we don't see anything. And we're trying to correlate that. Well, was it moving along the magnetic field line, or were we not in the wake, or are we not in some region where the disturbance would occur? But I think a goal is to see a 1 millimeter type object from the ground. That's the real goal. And then the next one would be throw up a few electric field satellites measurements that are just searching. But it's a lot easier to have something fly through a whole volume from like a radar transmitter or illuminate by sunlight than to try to go around and have this localized sensor to measure stuff. So I can't give you a good answer, but it's 1 millimeter and I would say at least a proximity sensor of 100 kilometers would probably be much better than they have now. Okay.
All right, any other questions for Professor Bernhardt? Oh, there's one up there, and...
Why don't we just keep the microphone between those three people there? Anyway.
One of the things, as far as I think lots of people have heard about, is debris and trying to get rid of it. And you alluded to that a little bit. Is that possible? Who's doing it? How can it be supported?
Well, as I said, I use the catcher's mitt analogy. You fly a big mitt, and there's all these baseballs, and you try to grab them and chuck them in your bag and grab another one. I don't know. There's some schemes that I've heard of that are proposed, but I haven't heard of anything that's working. That's actually. I don't know. People are looking into that.
What would be some of the proposals? I mean, just what's out there?
There's one proposal from the Naval Research Lab to inject dust particles, small dust particles, and all the space debris goes in one direction because you launch, you know, from west to east just to get a boost from the rotation of the Earth. And so launch dust particles go in the other direction, that you go into this forest of dust that then slows you down and then it deorbits. Something on that order. So those are the ideas. You know, just get rid of it. You know, once it gets to a low enough altitude, the drag is so much that it's gone. So somehow get it to a lower altitude. Okay.
Thank you.
Another question, right here. Okay.
Well, just to follow up on that question, when they use ion propulsion, that's a form of plasma. Has there been any thought to using something like plasma generation or excitement from, say, HARP or another source to actually affect the motion of some of this debris? Like,
To me, that's impossible because it's like a flea trying to move an elephant. You know, the impact of HARP is on a plasma like the ionosphere. You know, it hits the ionosphere, and the ionosphere by itself has such low density. So you need something bigger. You know, HARP works in a vacuum. You know, that's why I always say I work in a vacuum. You know, the ionosphere is a very low dense plasma that you hit it with high power radio waves, and anything that HARP does would not affect the space debris. So you need something more powerful.
All right, any more hands in the air? Oh, there's one over there.
Let's see. Oh, uh-oh.
Hi, I hope I can articulate this question well. But you said one of the future efforts will be to develop machine learning algorithms to detect these signatures. And you also said sometimes these satellites, even though it pass by in close vicinity, they do not detect these signatures. So I wonder, for specific satellite like Starlink, how characteristic is the signature across different latitudes where magnetic field line is changing, its direction is changing? Is it pretty standard across different parts of the orbit?
And that's sort of why we need somebody who works on machine learning. In other words, you make a bunch of measurements and then, okay, group the ones you didn't see, group the ones you did see about their both frequency domain and their time domain signatures, and then sort them out that way. And we haven't done that. So that's something we need to do in the future. Is there anybody here that works on machine learning? Oh, yeah. Oh, anyway, so that's why I addressed this to the expert in machine learning. Okay.
Any more hands in the air?
We have some more from online.
Oh, great.
So Christopher Jacobs on Zoom asked, can you use magnet waves to generate eddy current to slow down the debris so it will have to slow down and then burn up?
So the idea, it's a great idea. I'm going to patent it immediately. So you have any piece of metal and it goes through. However, if you draw a current through it, a J cross B force, that's the J interacting with the magnetic force, would cause a force to possibly slow it down. I don't know how to do it, but that's a great idea. We should pursue that. And maybe your HARP idea. Maybe we could use HARP to induce some current into the piece of metal and then interacting with magnetic field, and it's gone. So you guys are both co-patentees on this idea immediately. Okay, it's a great idea. I'll think about it a little bit more. It sounds like a great idea.
And then another question on Facebook from Dale P. I was in NORAD in 1979 at that time. They said they watched space debris the size of your fist. What size is the smallest debris we watch now?
Yeah, you can see, if you're clever, I think down to 10 centimeters, and maybe down to 1 millimeter. Or I mean, down to 1 centimeter. Down to 1 centimeter is sort of what you can see now. And then below that, it's sort of invisible. It depends on what sensor you're using. But I also like to mention why light versus radio. Anybody know what Rayleigh scatter is versus Mie scatter? Good, then I can explain it. Me-scatter is a wavelength that's comparable to the size of the object or smaller. Like light is so small, it's usually me-scatter. Rayleigh scatter is a wavelength that's this big and the object's this big. And it turns out it doesn't see it. And so for the scattering techniques, we want to make an object that is this big if our radio wave's this big. Well, the plasma wave techniques takes an object that's 1 meter and makes a ball that's 10 kilometers in size. So it actually increases the size of the object in terms of waves. Now you just have to find the right wave to interact with that 10-kilometer object to scatter. So that's the concept.
All right, any more questions? Any from online? Any hands up in here? I can tell it's an interesting topic. All right. All right, let's wrap it up. Let's give Paul a big hand for a great presentation tonight. And great questions from the audience here and from our audience online. We appreciate that. Let me say thanks to everybody, especially our sponsors, and to tell you about next week. We hope we can see you back here, same time, same day of the week, for our next science talk, Inspiring Girls Expeditions Alaska, Teaching Science and Art with Nature's Guidance. And with that, I think we'll call it an evening. Thank you very much, and be safe on your drive home.
You did great.